Okay, Bismillahirrahmanirrahim. Yesterday we've looked at phenol, and then um, we also noted that phenol is a slightly um, acidic. It is slightly acidic, so it is considered a weak acid. Um, it is certainly more acidic than water and ethanol, okay, or any types of alcohol. So even though these compounds are generally not treated as acidic like water. We never say that water is acidic, but because water can dissociate to give out H plus, that is a characteristic of acid. Okay, even though that this dissociation happens very, very small, at a small percentage, but because it releases hydrogen ions, it falls under the definition of acids. Okay. The strength of acidity depends on the stability of the anion. If the anion that you're forming is stable, that means more anions form, more dissociation, more acidic. Okay, so we looked at two explanations yesterday, and then I was just looking at the marking scheme, and I found that explanation number 2 is more frequently used as an answer. Okay, explanation 1 is not so much, but there's also another explanation which I have not mentioned. So I will ask you to add that later on to your notes. But first, I just want to go through explanation 1 again quickly. I'll talk about the diagram that that got you confused at the end of the lesson yesterday in a minute. So explanation 1 says that because the lone pair of oxygen here aligns or overlap or is parallel with the delocalization of the benzene ring, essentially the delocalization of benzene ring is extended. Okay, so what happens is that the negative charge that initially belonged to oxygen alone is now spread out to the whole molecule. Okay, so you can imagine that the negative charge is not as strong in a way. Okay, it's not as strong. So if the negative charge is not strong, if you look at the dissociation equation, it will not attract H plus. Okay, so it will be stable. It will be stable as it is, C6H5O minus, right? If the negative charge of the anion is strong, it attracts the H plus, so the reverse reaction will occur. Okay, that's explanation number 1. Explanation number 2 says that phenoxide is a stable anion. Okay, phenoxide versus phenol. Now, if you're wondering what a phenoxide is, I don't know if I mentioned it to you yesterday. Phenoxide is the ion when we lose H plus from phenol. That's a phenoxide. Okay, that's phenoxide. Hydroxide, OH minus, C2H5O minus is ethoxide. Okay, the anion of ethanol after they lose some hydrogen ions. Okay, now why is a phenoxide a stable anion? Okay, the idea is if the anion is stable, that means a lot of ionizations will occur, more acidic it will be, right? The reason for this is, again, for the same idea, the negative charge on the oxygen is being delocalized over the whole ring. It is being spread out over the whole ring, okay? Explanation number 3, which is something that is more frequently used in answers. Okay, remember, ionization involves the breaking of the OH bond. Yeah, you see that? During ionization, C6H5OH, the OH bond is broken to form anion and H plus. Okay, so explanation 3, if you add it to your notes, okay, it's talking about how easy it is to lose the H plus. Okay, so the idea is if it's easy to lose H plus, more acidic. If it's harder to lose H plus, it's less acidic. I hope that's a more easier concept to understand. Okay, so now explanation 3, when the lone pair of oxygen is delocalized into the benzene ring, OH bond, remember the hydrogen bond is this hydrogen is the one that is lost as H plus. Okay, OH bond is weakened. Okay, therefore it is easier to release. Hope you can see the handwriting. To release H plus, therefore more acidic. Okay, so this explanation number 3 helps to explain the diagram yesterday. Okay, I'll draw it again because I don't have it in on my slides, but it is in my notes. O minus, okay, maybe I'll use a different color for that, red. Okay, now this arrow, the red arrow, is showing that the lone pair of electrons is being delocalized. Okay, it's delocalized into the benzene ring. In a way, here benzene ring is said to have an electron withdrawing effect. Okay, so benzene withdraws the lone pair of electrons on oxygen. It doesn't completely take it away, but it's just, it takes it for delocalization. So the electrons are now moving not only inside the ring, but also towards the oxygen as well. So technically oxygen hasn't lost its lone pair yet. Okay, it's just that it's constantly moving around. Okay, so this arrow is what we mean by the lone pair of oxygen is delocalized into the benzene ring. Or you will see some text that says the benzene ring has an electron withdrawing effect. It withdraws the lone pair of oxygen into the ring. Now, although the word withdrawing sounds misleading, as if it sounds like the benzene ring is taking away the lone pair of oxygen, actually it's just being moved around to be shared. The oxygen still has its electrons, but now it's mixed with the pi electrons in the benzene ring. Okay, so phenoxide will still have its negative charge. Now, even though the negative charge is being spread out into the over the whole molecule, the negative charge is still there, just not as strong at attracting the H plus. Okay, now moving on for ethoxide. Okay, so ethoxide is the anion of ethanol. If you look at this equation, okay, so ethoxide, it has a negative charge on the oxygen still, okay, but this negative charge is not being moved around. This negative charge stays fixed on the oxygen. That's one, okay? So that negative charge is very strong. It can attract H plus. Okay, if you look here, this negative charge is strong. It attracts the H plus. What happens? It favors the backward reaction, therefore less acidic. Okay, in order to have a more acidic, we want the forward reaction. We want more ionization, not the opposite. Okay, that's the first explanation. The second explanation is regarding the idea of stability of anion. Okay, it's easier to talk about the stability of the anion. Now we have a negative species, okay, and then on the oxygen there is an ethyl group attached. Now from AS you already know that ethyl alkyl, whether it's methyl, ethyl, propyl, butyl, they have an electron donating effect. Okay, so you will see this arrow here. That means the ethyl group will donate more electron density onto the already negatively charged oxygen. Okay, so you just imagine you're already a negative person and then someone donates negativity to you. You will become even more unstable. Okay, so this anion is unstable. It doesn't like to be formed. Okay, now because it is unstable, we don't want to form them. That's why you don't have a lot of dissociation happening. You don't form a lot of this anion. Okay, I hope that is easy to understand. Now, moving on to question 2.1, describe and explain how the acidities of ethanol, ethanol and phenol compare to that of water. So you have 4 marks. Oops, you have 4 marks. I will give you the answer here. This is based on the marking scheme. Okay, first you have to compare, you have to talk about the acidity first. Okay, describe who is more acidic than water. Now, understanding the question sometimes can be difficult, okay, because it says describe and explain how the acidities of ethanol, phenol compare to that of water. Actually, they want you to talk about ethanol versus water, and then phenol versus water. Okay, so most of the time that students aren't able to answer questions is not because they do not know the answer, it's because they do not understand what the question is asking. Okay, so please understand when the question is written down like this, they want you to compare each of these molecules with water. Okay, right, so let's have a look. First, we talk about ethanol versus water. Water is more acidic than ethanol, and you know that water is already neutral. That means ethanol is very, 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 very weak acid. Okay, now, why is water more acidic than ethanol? Okay, so the term that they like to use, the term that they like to use is due to the positive inductive effect of C2H5 group, or C2H5 gives electron to oxygen or intensifies electron in OH bond. Okay, so which one is the easiest? This one, I would say this. Okay, C2H5 is an electron donating group. Therefore, it gives electron density to the oxygen. Okay, so C2H5O minus becomes unstable. Okay, so you can see that there are several explanations that you can use. Due to the positive inductive effect, this one, I do not like to use this term because it can be confusing. Okay, because C2H5 is electron donating, but they call it positive inductive effect. When, if you think about it, electron donating is, you know, a negative effect because you're supplying negativity. Okay, the other one intensifies electrons in OH bond, that I haven't mentioned to you yet. It's basically about you donating electrons to the OH bond. The OH bond becomes stronger, so it becomes more difficult to break the OH bond, hence less hydrogen ion is being given away. Okay, so 1 mark for saying water is more acidic than ethanol. Please write this in words. Okay, do not write it like that as a mathematical term. Write it in words. Water is more acidic than ethanol. The second one, Phenol is more acidic than water. Again, write it in words, right? This is the marking scheme. Do not follow the marking scheme. Of course, they try to make the marking scheme as simple as possible so that the marker finds it easy to mark. But for students, you need to write it down in words, okay? Why is phenol more acidic than water? Due to the stabilization of the anion, okay? So I will take the first answer. The second one is a little bit complicated, okay? Stabilization of the anion, because the lone pair of oxygen is stabilized into the ring. No, it's delocalized, sorry. Is delocalized into the ring. So that makes your phenoxide stable. Can't spell. Okay, so as I said, if you don't like this kind of explanation, why one is acidic more than the other, you cannot run away from it, because in the next topic, you will have to explain about acidity again. And frankly speaking, they like to ask about acidity. It's quite frequent. Just now when I look at the question paper, there was one in 16, 17, 18, and even 19. So every year they like to ask about acidity, okay? Right. Now moving on, okay, place the following molecules in order of their acidity, starting with the most acidic to the least acidic. Now, if you look at this list, the strongest acid is HCl. Of course, that's the only strong acid in this list. So we start with HCl being the most acidic. And then you have carboxylic acid, which is an acid, so that wins. Alcohol, which is not an acid, we don't see it as an acid. Water is, as we know, neutral, so we'll leave that first. And then we have a phenol. Okay, so after we start with the strong acid, we move on to the weakest acid that we know, which is carboxylic acid, CH3COOH. Okay, so we're left with phenol, alcohol, and water. So we know that phenol is more acidic than water, with the alcohol being the least acidic. Okay, I know this time it's propanol. It's still the same as ethanol, methanol, butanol, and etc. Okay, right. So I'm going to move fast now, because I didn't intend to spend a lot of time on this part, because we've already covered this yesterday. Reactions of phenol. So now, if you remember the structure of phenol, as I mentioned last time, there are two functional groups in phenol. One is the hydroxy group, and the other one is the benzene ring, or the arene, aromatic ring. Okay, so when we look at the reactions, chemical reactions of alcohol, you have to make sure you look at which functional group is reacting, okay? If it reacts with the OH group, it's the alcohol group. The reaction is slightly similar to alcohol, okay? Reactions of the aromatic ring is the one in the benzene ring. So it's similar to your benzene or methylbenzene, more or less, okay? Now, the OH bond, not only it is similar to an alcohol, but remember the OH bond is also where the acidity of the phenol comes in. Okay, so so you would imagine phenol reacting as an acid due to this OH bond, okay, because during dissociation, it is this OH bond that is being broken. Okay, so phenol has an acidic property, and so as you know that acids will react with an alkali. So that's the first reaction. Phenol can react with a base, sodium hydroxide, potassium hydroxide, to name some of the most common alkali or base. Okay, so phenol reacts with sodium hydroxide to form a salt and water. So nothing new here. Okay, the only thing that's probably new is the name of the salt. Okay, so we're all, just like hydrochloric acid with sodium hydroxide, you form sodium chloride. Okay, so here you form the sodium part from the hydroxide ion and the anion from your acid. Okay, if I draw this out, well, OH, okay, and then the OH bond is being broken, right? So you form, let me use a different color, plus Na plus OH minus, okay, to form, the anion of a phenol is called a phenoxide. Okay, so that's negative charge. You need a positive cation to counter it, which is sodium ion. Okay, so that's sodium phenoxide, and the other product is just water. Okay, so the sodium phenoxide has this structure. Basically, it's just like HCl plus NaOH, okay, where you form an ACl. Cl minus comes from the acid, but in this case, the anion comes from the acid. Okay, so I will not go into details for that one. Next one is phenol reacting with sodium. Okay, so this is similar to that of alcohols. If you go back, revisit your AS notes of alcohol, alcohol can react with sodium. Okay, so phenol can also react with sodium. Right? Phenol reacts with sodium to form an ionic salt, same thing, and hydrogen gas. Okay, so basically this reaction is the same as the previous one, except this time we're using sodium metal. Okay, now if you react an acid with a metal, you get hydrogen gas. Okay, but this one, not just any metal, it's specifically sodium. This reaction of ethanol plus sodium is actually a distinctive feature of ethanol. That means you can use it as a test for alcohol, but don't be fooled, because carboxylic acid can also react with metal because it's an acid. Acid react with metal will give out hydrogen gas. Okay, so far you know that alcohol can react with sodium, carboxylic acid can react with sodium, and now phenols can also react with sodium. So this is something that you have to memorize. Okay, that's the only reaction that is happening on the OH group, reacting with base and reacting with sodium. Now we move on to the reaction on the benzene ring. So it's slightly similar to the reaction of your benzene. Okay, so now we're looking at the reactions of the aromatic ring. In your notes, I have categorized them as well. On page 3, it says A is reactions of the OH group, and then on page 4 onwards, it says B is the reactions of the aromatic ring. So the reaction will happen in the ring. Now, the ring acts slightly like benzene, but there's an additional OH group. Okay, and this OH group, as you know already, that the lone pair of oxygen is being donated into the ring. Okay, when it says OH group is electron releasing, you can see it as lone pair of oxygen atom is donated into the ring. Hence, you see this arrow. Okay, the lone pair is being delocalized into the ring. It means the same thing. Okay, the terms the lone pair of electrons is delocalized into the ring, or the lone pair of oxygen atom is donated into the ring, or electron releasing, they mean the same thing. Okay, now that means your benzene ring, which is already rich in electron density above and below the plane, now becomes richer. It has a higher electron density. Okay, I'm not talking about the charge or anything here, just the what do you call this? The intensity of the electron charge, okay, the electron density. So now the ring becomes more electron rich. So electrophilic substitution reaction is much easier to attack, okay, right? What this text sentence is saying is that now the ring becomes more richer, okay, it becomes richer in electron density, therefore attract electrophiles better. Okay, so this is the same as methyl benzene. Methyl has this electron donating effect where it donates its electrons into the benzene ring, so the benzene ring now becomes richer. Okay, chlorobenzene is the opposite, right? I will just mention briefly, we've already looked at this. Chlorobenzene has the opposite effect. The chlorine pulls away the electron density from the ring. Okay, hydroxy group of your phenol pulls electron density into the ring. So you can see these two opposite effects. Okay, now because you are donating more electron density, the ring becomes richer, more negative, if you think about it. Okay, chlorine has the opposite effect. It takes away some of the electron density from the benzene ring. So now this benzene ring doesn't attract electrophiles as well as your phenol. Okay, so we've talked about chlorobenzene in the previous topic already. Okay, let's have a look at the reaction. Bromination, just like your benzene, benzene can also go bromination. Phenol goes through bromination just like benzene, except that because phenol is already reactive, phenol is much more reactive than benzene. Phenol doesn't need a catalyst. Okay, for benzene, if you want to brominate it, you need a halogen carrier as a catalyst, which is aluminum bromide. Here, you do not need a catalyst because phenol is already reactive. It attracts the electrophile nicely. You don't have to force it. Okay, so phenol reacts readily with bromine without a catalyst. It is so reactive that multiple substitution takes place. Okay, for benzene, first you only have mono substitution. Okay, in phenol you cannot help it, but tri substitution happens. Okay, so this works for chlorine and iodine as well. Okay, tri substitution will happen. So because OH is an electron donating group, it activates the 2,4,6 position. I forgot to mention this to you, but it was written down on your notes. So OH is electron donating, therefore it activates the 2, 4, and 6 position. Oops. That's why your bromine, without any catalyst, without heat, at room temperature, they react like crazy and substitute the hydrogen on the 2, 4, and 6 position. So now we call it the 2, 4, 6 tri-bromophenol. Okay, and an observation that comes with this is that bromine is orange color. Orange or brown, orange or brown. and the rest is the HBr is colorless. Okay, this tribromophenol has an appearance of white PPT. Okay, the 2,4,6-tribromophenol is a white solid. So the observation you will see here would be, first, the decolorization of bromine. So orange or brown bromine decolorizes. And secondly, white PPT is formed. Okay. So no catalyst needed, and automatically all the 2,4,6 substitutions are being used up or being replaced by the bromine. Okay. What's next? Okay, last one. We have 6 minutes left, so I'm going to go really fast with this. Now, benzene also can undergo nitration. Okay, with benzene, you need a nitric acid, concentrated nitric acid, and concentrated sulfuric acid, and at 55 degrees Celsius. Okay, now all these things are not needed for phenol. As I said, phenol, the hydroxy group donates electrons into the ring. The ring is now electron richer than benzene, so it attracts electrophiles nicely. You don't need a catalyst for it. Okay, so what happens then? Phenol can react with nitric acid in two ways: when you use dilute nitric acid or when you use concentrated nitric acid, but still no catalyst, no heat is needed. Okay, now when you use a dilute nitric acid, of course the reaction will be gentler. I mean, it's much more reactive still compared to benzene, but dilute and concentrated, you would imagine that the one using dilute nitric acid would be a gentler reaction, and the one using concentrated acid would be a much vigorous. Okay, so that's what happens when you use dilute nitric acid. Mono substitution happens. Okay, mono substitution means you only substitute one hydrogen in the ring. Okay, when you use concentrated nitric acid, tri substitution happens. Okay, that means all the three positions that are activated, the 2, 4, and 6, they're all being substituted with nitro group, NO2. So this is what you have on your notes. Okay, let's have a look at the dilute reagent first. Okay, when you use dilute nitric acid, you can take up either the 2 position, 2-nitrophenol, or 4 position, 4-nitrophenol. So only one mono substitution at a time, but 2 possible products. Okay, now you may ask me, what about the 6th position? Now, if I put it in the 6th position, 6-nitrophenol is actually the same as 2-nitrophenol. Okay, same as 6-nitrophenol. We take 2 as the smaller number. Okay, now if we look at the concentrated, so if we use concentrated nitric acid without catalyst, without heating, the reaction can happen. Okay, if this was benzene, it cannot happen because the ring of benzene is not reactive enough, not as reactive as phenol. Okay, so when you react phenol with concentrated nitric acid, all the 2, 4, 6 position are being used up. Okay, tri substitution happens in one go. Hence, you get a 2, 4, 6 tri-nitrophenol. Okay. Right, so let's see, what do we have after this? Okay, so the next one is diazonium salts. I do not want to rush that because that's definitely something new for you. Okay, so any questions before we go? We have less than 3 minutes left. If you have any questions.
Miss,
Mm-hmm.
I still don't understand about the Cl in the difference between Cl and OH.
Okay, so Cl, it has the opposite effect. Cl pulls away the electron in the ring. Okay, so actually Cl is from the previous topic. Okay. Now, this ring has electron. Okay, we say it's electron rich. Cl has the ability to pull away the electrons from the benzene ring. Okay, so what happens? This one, the arrow is going to Cl. Okay, if you compare here, electron is going away from the ring. Here, electron is going into the ring. Now, when you add electrons into the ring becomes more electron rich. If you take away electrons from the ring, now the electrons become less, the ring becomes less electron rich. Okay, how chlorine does that? Well, thankfully, okay, for you, you do not have to understand that process. You just need to remember that chlorine pulls away electron density from the ring. Okay? Is that answering your question, Safina?
Yes.
Yeah.
Yes.
So just think of chlorine as having the opposite effect to your phenol. Okay? How it pulls away the electrons, you don't have to worry about that. Okay?
Thank you, ma'am.
Okay, you're welcome. We have less than a minute left, so I think we'll get cut off anytime soon. If you have any more questions, please ask in the group, okay? Or if there's anything that's confusing in your notes, please let me know, okay? Right, Assalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.
Thank you.